We are going to get a presentation from Marianne Bellotti. Now, Marianne, she works in the fascinating intersection of legacy systems and security, which I can imagine is a very interesting place. She's also the author of a book, Kill It With Fire, and she runs a blog. But today she's going to tell us about formal verification of systems. Marianne, the stage is yours.
Hi, everybody. A great fun to be here today with you, talking about one of my favorite topics, which is modeling systems using various methods of formal verification and formal methods. So just a quick overview of who I am. Depending on how you count, I've been in the software industry for over 15 years. I say depending on how you count because like many of us, I started my career in software and 13 as a script kiddie on the internet. And so I'm not sure that most of that counts. So I tend to just go by when I formally got my first job as a software engineer a little bit later in life. In between my script kiddie days and my professional software career, I ended up taking a degree in anthropology. So I kind of am jokingly referred to as the technical anthropologist because so much of what I do is about thinking about how technology functions within groups of people and how groups of people and how they self-organize affects both the technology that they build and their ability to maintain it. For most of my career, that meant that I gravitated towards legacy technology because legacy technology is all about what was the organization like and what were its challenges when we built it versus what our challenges are now and how did the technical debt accrue across those lines and how do we restore things to operational excellency. And this year, I put out my first technical book, Kill It With Fire, which is all about making the techniques that are really good with dealing with legacy modernization accessible to all sorts of software engineers, because they're also really useful when you're building new technology. A lot of what I'm starting to do now, I turned a new page in my career, and I'm now focusing largely on complex systems, not just old systems. And for me, it's virtually the same type of work, right? There's very little difference, I think, between what I used to do around legacy modernization and what I currently do around complex systems. It's just it appears on the surface to be different. A huge part of what I do, whether I'm working on an old system or a new system, is modeling systems. And I think before we go into all the different types of technology that exist, and I want to give you an overview of what's out there, what they're good at being used for, what they're good at representing, and also where we still have to go, what the future of this type of work is. But before I do that, I want to clarify, what do I mean when I say model? Right? So there are lots of different definitions we could ascribe to the word model. But in the context of this talk, we're talking about an abstract representation of the interactions that make up a system. But the key part of it is that it's runnable, right? We could draw diagrams of all of the interactions in a system and create an abstract representation with Visio or things like that. But what we want is a diagram, a representation, a specification that is runnable. We can set constraints, we can set assertions, and we can have a model checker tell us whether or not, given the specification that we built, that system can pass those checks or not. So that's really what we're describing in this talk when I say the word model. So why would we want to model a computer system? Well, I think we've all had a scenario in incident response and maintaining our systems where something has gone horribly wrong and triggered some sort of massive failure or outage. And when we did the triage, we found there was a configuration change or a memory issue that in retrospect seemed really, really obvious. And we don't really understand why it took a huge failure for us to actually figure out that was hidden in our infrastructure. Fundamentally, we don't know what we don't know. So what's really great about modeling and why I encourage people to sort of explore this area is that before you write any code, it allows you to sort of play around with different concepts and run simulations about how these systems will behave under different conditions. And that gives you a little bit more visibility into that unknown area where there might be problems. So we get to explore different scenarios. We get to look at our expected behavior, define our expected behavior, and then have the computer sort of deduce if that expected behavior ever leads to unexpected behavior. We have to go further to like define what we think impossible states on that system should be. And then we get to verify whether there are any conditions which would lead to impossible states. And those models help us find all of those known unknowns. So where does software tend to go wrong? Like what kind of things would you want to model, right? So the types of unknowns that we're really thinking about when we're talking about modeling are things like algorithmic correctness. Does the algorithm we've written do what we expect it to do in the correct way? And does it do it in like all possible cases? Concurrency, if the order of events within a system change, does that change the outcome in a significant way? Relational, and when we're talking about relational, we're not really talking about relational data so much as we're talking about hierarchies of permissions and roles and groups and how systems relate to one another. And then the last area is feedback loops, right? As the system continues to operate and do the same functions over and over again, is there something that accumulates that changes fundamental behavior? And so we're going to start with algorithm correctness, right? Does the algorithm do what it's supposed to do? Does it do for all possible inputs? Are there any undefined states in either in the program language design or in the application itself? And so one of the tools that people use for algorithmic correctness is a formal verification language called COC. There is always a conversation about whether or not they will change the name of this language, because obviously Americans have a very strong reaction to it having this name. But for right now, the name of this language and the correct pronunciation of it is COC. And COC is a proof assistant language. And so what that means is that it helps you build mathematical proofs of software, or really you could build mathematical proofs of anything you wanted to build using a domain-specific language. What's interesting about COC is that it has some ability to do what's called program extraction, which means once you have built the proof and you've run it and proved the things that you were looking to prove, you can actually then take that and compile to some languages. OCaml and Haskell are the big ones. There are some other languages that allow you to directly compile from a spec. And it allows us to do this kind of lab logic around, like, for all natural numbers, is this algorithm correct? Which is a little bit beyond the type of testing that most software engineers are used to, right? Like we're used to this idea of like, well, we run our unit tests to establish that known inputs produce known outputs, and that known errors produce the errors that we expect. But we don't really think about like all possible inputs. And this is how we kind of assess that. So one way to think about how these kind of math problems tend to work is with type systems. If you know anything about type systems, then you know that what a type system really is a logical set of rules defining what a type can do and what a type can't do. So we have this question of like, in our programming language, can we add an int and a float together? And what happens when we do? And in some languages, the answer to that question is yes. And in some languages, the answer to the question is no. And it's determined by the set of rules in the type system that tell the compiler, okay, this is what you do when input A is an int and input B is a float. This is, you either convert the int to the float, or you error, or you do this, or you do that. And so it's a set of logical rules that define what the behavior should be. And this is sort of the same principle that a lot of these formal verification systems operate under, is that we should be able to prove mathematically that A plus B plus C is equal to the value of C plus B plus A without running every conceivable value. Like, we should be able to prove that relationship rather than just run 100 tests proving it. Then we move on to like concurrency, this idea of like, what do we do if the steps of the algorithm are in a different order? And more specifically, if we put controls in place to keep steps from being run out of order, are they going to work, right? Are there circumstances in which those steps will fail and we will end up with a poorly defined or undesirable state, right? So the classic example that we use when we start to teach people about this type of formal verification is the overdrawn bank account, because it's really easy to conceptualize how we can approve a transaction to pull money out of a bank account before, like the race condition scenario, before we've really accounted for all of the transactions, and end up with a negative balance, right? So the favorite tool for these kinds of problems is a system called TLA Plus. And what TLA Plus does is it's a first order logic language that allows you to define an algorithm in a series of steps and then set constraints as logical rules. Logical rules like this is always true, this is eventually true, so on and so forth. And then what it does is it runs your algorithm in all sorts of different orders of steps to find out if there are any pathways in which outcomes violate those logical constraints. All right, relational. And so I mentioned before that relational can involve things like data schemas, relational data, but it doesn't have to. It's anything that has kind of a hierarchical relationship. So a lot of what I use this kind of modeling for are security things like permission groups, roles, inheritance. Like how do we know that our fine-grained permissions don't accidentally expose data to the wrong person? You can also use it for system-to-system interaction, because we can also make that look like a hierarchical relationship. And so the tool that's really good at doing this type of modeling is called Alloy. It allows you to create what are called signatures, which I sometimes describe as kind of like objects, because I think that more clearly gives people an image of what they are. But they're essentially types of things that you are defining relationships between. And then the assertions that you're writing are about the valid relationships that two signatures can have within a model. And what backs Alloy is an SMT solver. And a lot of formal verification ultimately compiles down to either SAT or SMT solver, which is all about boolean logic. If you are unfamiliar with SAT and SMT solvers, the best way to think about them is like logical puzzles. The classic example is Sudoku. Like Sudoku is a puzzle where each little square in the overall puzzle has a state, a set of possible states, and then one state that is actually true given all of the conditions. And when you build a Sudoku solver, essentially what you're doing is you're saying these are all of the possible states, and these are a subset of states that I know to be true, and from this information that I know to be true, deduce all of the other states. And so that's what we're doing when we're using formal verification for the most part, is that we're looking at like defining all of the possible states, defining a set of states we know to be true, and then using the computer to run all sorts of simulations that determine what states must be true or must not be true given those conditions. And then the last area that's sort of more on the edge of it is feedback loops, right? Because as we deal with more distributed systems, a lot of the practical problems people have in technology looks like feedback loops, right? Like I, as a software engineer, am very unlikely to write my own version of the Praxis algorithm. I'm far more likely to like download an open source library and like integrate somebody else's work into the kind of algorithm design. Most of the problems that my teams are going to have are going to look like we have a load balancer that is constantly killing unhealthy servers and triggers an outage. Or we rolled something back and that triggered some sort of problem. Or we freed memory and that triggered some sort of problem. Or we don't have correct incremental back off. And so we are like essentially DDoSing ourselves by constantly retrying a request, right? And what's interesting about feedback loops versus the other problems is that the action itself is not problematic. We want load balancers to be able to kill unhealthy servers. We want to be able to roll things back. We want requests to be retried. But the context with other interactions is what the problem is. And so what's really important to understand about formal verification is what the difference between an impossible state versus undesirable state on a given system. And this is like how I get people started. When we're talking about a system and you're starting to develop that spec, what you really want to write the spec to is the impossible states. You want to figure out like what should not be able to be reached from within this system, either what states will the code not be able to reach or what states should the user not be able to reach, and defining those really clearly in terms of logical rules. And then kind of building your spec around that so that that's what your model checking is. If you try to write specifications based on feedback loops and undesirable states in a lot of these tooling, it becomes very, very difficult to get a working spec that's really useful because they're really strongly geared towards impossible states over undesirable states. Okay, so this kind of brings me to some of the work that I've been doing in this space that I'm really excited about. So Wright Forrester is one of the kind of original legends of computer science, right? He was operating in that really explosive period of time in the 40s and the 50s when computers were just starting to become real technology that was accessible to academics and institutions. And there was just so much that needed to be built. So there was low-hanging fruit everywhere about figuring the best ways to do things. He was principal in developing magnetic core memory, and most of that work and his later work led to the forerunner of developing a RAM. He's got all of the honors that you would bestow on a computer science legend. And what's interesting about him is that around in 1956, he made the decision to transfer away from the engineering side of MIT into their business school. And the reason why he did this is because he felt like he had solved all the hard problems in computer science and there were no more problems left to be solved over there, and he wanted to go solve some other problems somewhere else, which is a funny statement if you think about it in retrospect. Obviously, there are many other hard problems to solve in computer science. But he coined the term system dynamics. And his goals with system dynamics were to create a control theory for economics. And so how he got started with this is that GE approached him as a computer scientist to sort of solve their inventory problem, right? They said, hey, we have this problem where we either seem to always have too much or too little inventory on hand. And we've heard about these computer things that do all these calculations. And we feel like the computer can solve this problem for us. The computer can tell us exactly how much inventory to order so that we always have exactly as much as we need. And when he looked at this problem, he realized that it was very similar to a problem he had seen when he was serving in the military around aiming cannons, right? That the first shot was a missed shot. And then the second shot was still a missed shot, but it was a complete overcorrection of the first mistake. And that generally speaking, when they were aiming these large weaponry, that they would kind of oscillate between overcorrecting, undercorrecting until they got close enough to actually hit the target. And the way they solved this problem was with control theory. They basically factored into the calculation that these things don't exist in a vacuum. And for every force that you're exerting within a given system, there are some counteracting forces and there are some intensifying forces. So there are some counteracting forces that are limiting and restricting the change, and then there are intensifying forces that are amplifying the change. And you need to be aware of what those are for the given thing that you're trying to accomplish and calculate them and factor them into your calculations in order to aim your cannon correctly or steer your ship effectively. So if you're steering a ship, you've got the force of the waves, you've got the force and direction of the wind. All of these things are going to affect how aggressively you need to steer the ship in order to turn it and get it on the right direction. And so his thought process here was well, we can do this with mechanical systems because the forces are known and they're calculable, we have sensors. But how much force is in a price rise, right? So he developed system dynamics in order to try to incorporate some of the thinking behind more engineering discipline of control theory into more nuanced areas like business, like policy. And what I find interesting about his work is that I think we've actually reached the point in the development of systems where some of what he built and this philosophy is actually a useful tool for the feedback loop problems that we have. Because how much load is in a single page view, right? We can, in theory, calculate that. But that's an estimate, that's an average. It's very hard for us to deduce when we make a change in a distributed system, like what the counter forces are in those feedback loops, right? How much load in a single page view might depend on your cache settings, right? Like, is there a cache at all, number one? And how often does it refresh? Right? It might depend on daily code updates, right? It might depend on a lot of different factors that are hard to it's hard to produce a calculation that will really get you solid results as you're trying to aim things. And so the way system dynamics works is it has these two fundamental abstractions. It has stocks, which are stores of something, resources, memory, CPU, IO, things like that. And then flows, which are the rate of change of those stocks from one stock to another or from a stock out of the system. And so the conventional metaphor that we start people with in system dynamics is a bathtub full of water. Like the water in the bathtub is the stock. The water coming out of the faucet is a flow. The water coming out of the drain is another flow. And how the level of water that's in that bathtub is determined by the feedback loop in this system, right? How quickly the water is coming into the bathtub, how quickly it's flowing out of the bathtub, so on and so forth. So this is the basic of how we think about systems when we're using something like system dynamics. So how do we apply this for technical systems? Can we apply this for technical systems? We can look at abstractions in terms of we have resources. We know we have resources. They're not tangible in the way a bathtub full of water is, but we know that we have resources. Already mentioned CPU, memory, but we can also think about it in terms of number of requests. We can think about it in terms of the size of data that's coming across a wire. There are lots of ways we can represent these things in terms of stocks and flows there that kind of help us think about them. And what I find really interesting about this approach is that what is really critical in my mind for complex systems is finding the right balance between how complex the system is versus how tightly coupled it is. I often tell people that these are it's a trade-off, right? It's not possible to build a large system that is completely simple and loosely coupled, because when we try to scale that system, often what we do is we decouple parts and add more moving parts as a result. So you can think about if we have a web page that we want to scale, one of the ways we might scale that is by creating more instances of the same web page, adding complexity, and then putting a load balancer in front of it, adding complexity, but decoupling in general that request from that one server that might max out or might not. So that's sort of the balance that we see with systems, is that you don't have perfectly simple systems that are also loosely coupled. You can have simple systems that are tightly coupled. You have complex systems that are loosely coupled, or you have systems that are somewhere in the middle of that. And I like to have people think very strategically about where they're putting their complexity and where they're tightening their coupling. What's really interesting about this whole field is that when we have systems that are where that ratio is off, where it's tightly coupled and too complex, we tend to have really error-prone, difficult to maintain systems. And so Charles Perrow did a huge amount of work in this space around nuclear accidents and all sorts of what we would think of as mechanical or industrial engineering, and how when you look at the system and how it distributed the coupling and complexity, you sort of know that this system was doomed to failure. Okay, so the great introduction to system dynamics, if you're interested in reading more, is the book Thinking in Systems. It's very low technical, very accessible. It's actually written for policy people. And what I find really interesting about this book is she sort of highlights that the way one can represent stocks and flows in order to represent decoupled versus coupled systems. So it's a useful abstraction. I can go back to this example of like, okay, we've got a pool of virtual machines, and we want to know like the dynamics of the load balance, and we have like requests coming in and then requests being served out, right? And as we have a conventional load balancer, let's say, okay, if CPU utilization is more than 70%, then we want to add more VMs, right? And so we can really calculate like how many requests are we getting and the growth of our requests and like how that would impact our utilization and how that would lead to that behavior. All of that is like pretty straightforward, right? But then as we kind of run that simulation, we inevitably get to a place where, okay, we're over 70% utilization on one of our pool of VMs. What is the next state, right? Is the next state a 66% number, or is the next state 64% number, or is it something else, right? And the answer to that question really depends on like when the interactions of this load balancer, what is happening when, and how coupled are these actions together, right? Like, are we evaluating the load, spinning up a new VM, or are we spinning up a new VM separately from like how we're calculating, right? So we can represent these differently as like whether they are one flow changing two stocks or one stock per flow sort of scenario. And that allows us to flexibility of modeling different types of coupling in the same system. And as a result, we can sort of see which one we preference. So I'm going to wrap this up by saying like this is kind of an area where in doing a lot of research and doing a lot of development, there aren't great tools for actually doing model checking around system dynamics, and that's what I'm really interested in. So I've sort of been playing with building a domain-specific language specifically for this point. I have it upline if people want to play with it, but more importantly, I'd sort of been doing a podcast about my journey around writing programming languages and around modeling systems and like all of the things that I've learned as a result of this that I'd really love for people to kind of like check out and give me feedback on. And the things that I'm really interested in doing in this space are like supplementing the great tooling we already have around formal verification that talks with them about impossible states, with looking at those undesirable states, and in particular injecting the issue of probability to these things. Because a lot of times when we do formal verification, like all states are equal in formal verification. It does not matter to the model checker how likely an impossible state is. It's the fact that it's even that you are getting to an impossible state is the thing it wants to highlight for you. But when we're dealing with distributed systems, like we said, like these states aren't necessarily in and of themselves problematic. It's just in context. And so probability matters a lot to us. So I wanted to incorporate aspects of like, can we do model checking with probability? Can we model resilience? Can we like bring sort of a more formal tooling to the world of system dynamics? And it's been a fun journey so far. All right, well, that sort of concludes my formal talk. I'm more than happy to answer questions about different types of formal verification tools, different ways to sort of get into modeling, what I've been working on. If you want to follow my work, I'm available on most platforms under the handle Belmar, on Twitter, on Medium, as already mentioned. I really appreciate you guys giving me the time and space to kind of like geek out about this stuff.
Thank you, Marianne. Everyone, please go to the QA tab and ask your questions. Also, don't forget to rate the talk in the poll tab. And while we are waiting for people to actually type in their questions, I'm going to pop mine. This is a relatively new area to me. And in my civil life, I'm a reliability engineer, and it would never occur to me to actually try to evaluate all failure states, regardless of likelihood, because it's so expensive. And in your bio, I read that you work in a company that is in defense, and it occurred to me, which are the areas of IT where this kind of formal verification is especially relevant, and why is defense one?
So it's relevant everywhere. But it is much more common with embedded systems and with, I would say, aerospace engineering. It's always really fascinating to me going over to NASA and hearing like how they are evolving their software development process. because one of the reasons NASA's technology meshes so well with formal verification is that a lot of their software systems are very low to the low on abstraction layer, right? So they're not written in assembly. They generally write things in C, but they're not building like these really like high abstraction, object-oriented programs because they're going on satellites. They're going on space shuttles, right? And they're not like things where your everyday average user needs to interact with this software. And so as a result, they're very low in their abstraction level and much easier to verify. Well, and I think NASA's feeling is like, well, that the time has come to sort of incorporate a little bit more of a modern perspective. And I'm really interested in seeing how that advances, because once you start getting up to heavy abstraction layer type software, you start losing visibility into all of the impacts of a particular function, right? And so that is when verification becomes really, 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 really essential. So what was interesting to me about coming into the defense space, which was not a thing I thought I was going to do, let's say 2-3 years ago, is that I was in the private sector trying to get better traction around software development processes that accounted more for formal verification, and was getting a lot of great feedback about like, this is wonderful, we should totally do this. But ultimately we really like have our priorities with our business model and our sales cycle, and all of that was not being taken very seriously. But in the defense space, when you start talking to them about the importance of being able to verify that a piece of software does what it's supposed to do, that resonates with the customer on a much, much, much deeper level than it does in the commercial like software world, right? Like, because they understand what the impacts it could have if the software goes wrong. And so as a result, it gave me much more space and freedom to really invest time and energy into doing the work that I do with my engineering teams today.
Yeah, I can see that, because if my company's service is down for 2 minutes, then, well, it has all kind of financial and business impact for our customers, and it's really, really terrible, but it's not going to blow up in the middle of space.
Yeah, exactly.
So, and I am there to fix it. We have a question from Laszlo Hegedűs. Is that a certain level of abstraction worth using and not more? I guess he wanted to say, is there a certain level of abstraction worth using and not more? If yes, can this level be defined somehow?
So it's a case-by-case basis thing, right? The example I give you about abstractions are things like ORMs, object relational maps, right? So on one hand, this allows software engineers to not have to learn SQL and know all the ins and outs of databases in order to write applications. So it increases the speed to prototype, it increases the speed to new functionality. On the other hand, it's hard to write the most efficient queries when your queries are being auto-generated by an abstraction. You tend to get like a good, decent middle line, but there are ways of writing SQL queries that give you better performance and possibly better results that are difficult to represent in that abstraction and that you lose out on. You also, from time to time, will lose out on like ability to sort of comprehend what is going on when something is going wrong, because you don't necessarily have visibility into what the abstraction is doing. You really have to know like under the hood what that abstraction is doing really well to like triage some bugs. So with any kind of abstraction, you're going to have those trade-offs where it buys you a little bit, but it also costs you a little bit. And it's simply about like, what are your current needs and what makes sense for you?
Yeah, like with every kind of testing, you need to figure out how much to invest and what you are getting out. Yeah, it's a very, 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 very fascinating field. I'm coming from a mathematical background, so I like everything formal and well defined. And my frequent experience is it's just not always worth it. But sometimes it's a great tool. I'm not doing that kind of formal verification, other kind of formalisms I like. I think we have no more questions. So with this, then I would like to thank you again for your presentation. We have a little something for you that I hope my colleagues can show, and we hope to be able to ship to you.
Oh, wow.
As a token of our gratitude and appreciation. And thank you again for the brilliant talk.